Hi everyone, I'm Yue Zhang from Department of Electronic Engineering, Shanghai Jiao Tong University. I'm glad to present our work, VSANet Real-Time Speech Enhancement based on voice activity detection and causal spatial attention. This work is also in cooperation with Tencent Video Cloud. Speech enhancement is a fundamental task in speech signal processing whose purpose is suppressing environmental noise, thereby improving the speech's perceptual quality and intelligibility. Speech enhancement has been widely applied in various fields such as speech communication, automatic speech recognition, and hearing assistant devices. Traditional speech enhancement methods include spectral subtraction, Wiener filtering, probabilistic modeling-based methods, and so on. However, these methods always depend on specific prior assumptions and manual experience, especially in scenarios with highly non-stationary noise and low signal-to-noise ratio. The traditional method's performance is unsatisfactory. Recently, the deep learning-based speech enhancement methods have achieved great success. They can be generally divided into two categories, the time domain methods and the time frequency domain methods. The deep learning-based methods are data-driven, and deep neural networks have illustrated powerful feature representation capability and excellent generalization performance. The time-frequency domain methods are currently more widely used. They first convert the noisy speech waveform into the noisy spectrum by time-frequency transformation technique. The deep neural network is subsequently employed to process the noisy spectrum and perform noise suppression, resulting in an enhanced spectrum. Finally, the enhanced spectrum is converted back to the enhanced speech using the inverse time-frequency transformation. Time-frequency domain methods can be further categorized into mapping methods and masking methods. In our work, we adopted the masking methods. Given the noisy speech xn, where n represents the discrete time index, it can be represented as the sum of clean speech Sn and the additive noise Zn. Therefore, the goal of speech enhancement is to estimate the clean speech Sn from input noisy speech Xn. Different from the common methods that employ short-time Fourier transform for time-frequency transformation, we adopted the short-time discrete cosine transform. STDCT is a real-valued time-frequency transformation with implicit phase information, which avoids the phase estimation problem in the STFT-based methods and reduces the model complexity. The definitions of discrete cosine transform and inverse discrete cosine transform are presented in this page. In these two formulas, the mu represents the frequency bin and the n is the time index. Therefore, the above signal model can be rewritten in the STDCT domain as here. Subsequently, the predicting target of our STDCT-based method is the discrete cosine transform ideal ratio mask. And once the neural network outputs a predicted DCT IRM as hat M, the enhanced STDCT spectrum hat S can be derived by multiplying hat M with the noisy spectrum X. Finally, the enhanced speech can be obtained by ISTDCT. Next, we adopted the voice activity detection-aided multitask learning framework. As an important front-end processing module, VAD aims to distinguish speech segments from noise segments. Therefore, we believe that VAD can benefit speech enhancement. Specifically, correct labeling of speech and noise segments can help the speech enhancement network to completely suppress the signal of noise segments. Besides, it also enables the speech enhancement network to focus on feature learning of speech segments, facilitating better suppression of additive noise and better preservation of speech components in speech segments. The overall network architecture of our multitask learning framework is shown here. It comprises a speech enhancement module and a VAD module. Meanwhile, we adopt a parameter sharing strategy, which means that the speech enhancement module and the VAD module share the same encoder, while the remaining network is designed as a parallel dual-branch topology. This achieves a regularization among the two highly correlated subtasks, leading to better generalization and performance. For the speech enhancement module, it generally utilizes the convolutional recurrent network structure. The speech enhancement module consists of a shared encoder, a SE recurrent block, and a SE decoder. The shared encoder receives the noisy spectrum and extracts the high-level speech features. It includes multiple convolutional blocks, and the details of each block is shown as Figure B. Then the SE recurrent block receives the feature map from the encoder and models the temporal correlation in speech features. The structure of this block is shown as Figure C, which mainly contains several GRU layers. While the SE decoder is designed to reconstruct the low-resolution features back to the original imported spectrum size, it is composed of several transposed convolutional blocks and causal spatial attention blocks. The detail of each transposed convolutional block is shown as Figure D, and the causal spatial attention block will be introduced in the following contents. In constructed to the symmetric encoder-decoder architecture of the speech enhancement module, the VAD module adopts an asymmetric setting. The VAD module shares the encoder with the speech enhancement module and also includes a VAD recurrent block and a VAD decoder. Similar to the SE recurrent block, the VAD recurrent block is also used to model the temporal correlation, and the internal structure is shown in Figure E. Next, the output of the VAD recurrent block is fed into the VAD decoder. It finally generates the probability-like soft decision scores at the frame level. The detail of VAD decoder is shown in Figure F. As we know, the attention mechanism can guide the deep neural network to focus on important features while discarding unnecessary information, thereby boosting the feature extraction, representation, and modeling capabilities of DNN. In this paper, we introduced a lightweight causal spatial attention block and incorporate the CSA block into the skip connection paths and the SE decoder in the speech enhancement model, so as to assist in high-level feature extraction and feature reconstruction. The detail of our CSA block is illustrated in this page. To compute the spatial attention weights, we first apply average pooling and maximum pooling along the channel dimension to the input feature map U, and the two pooled feature maps are then concatenated along the channel dimension so as to obtain a dual channel feature map U'. Next, we adopt a causal convolutional layer, which first adopts an asymmetric zero-padding operation in the time dimension of U' to ensure the causality of convolutional computation. Subsequently, the convolutional resource is applied to a sigmoid function so as to obtain the spatial attention weights SAM. Eventually, the input feature map U is multiplied with SAM to obtain the final refined feature map. In our multitask learning framework, the total loss function is the weighted sum of the speech enhancement loss and the VAD loss. The speech enhancement loss is a joint loss, including both are LE loss in the time domain and are MSE loss in the spectrum domain. The VAD loss is the binary cross-entropy loss between the ground truth VAD label Y and the probability-like soft decision score Y hat. In this paper, we set the loss weights as here. They are determined by grid search. We conducted the experiments on the publicly available dataset named VSANet plus demand datasets. Additionally, to ensure the causality of model, asymmetric zero padding is applied for all the convolutional and transposed convolutional layers, and all the GRU layers is omnidirectional. To demonstrate the benefits of the VAD-aided multitask learning scheme and the CSA block to speech enhancement, we first construct a baseline model, which uses ST-DCT for time-frequency transformation and adopts the CRN structure as the network backbone, and it can be named as DCT-CRN. Based on the DCT-CRN, we respectively introduce the VAD-aided multitask learning scheme and the CSA block, so as to prove the effectiveness of the two ideas. As we take the DCT-CRN as the speech enhancement module and add a VAD module parallelly, we find the VAD-aided multitask learning scheme yields a better performance than the baseline model in all the evaluation metrics. In addition, we also try to introduce the CSA block to DCT-CRN, and the experimental results demonstrated that the CSA block can bring performance improvements. Eventually, our VSANet combines the above two improvements and it attains the best performance. We have also compared our VSANet with other state-of-the-art methods to objectively demonstrate the performance benefits of our VSANet. All the benchmark methods are also implemented causally. Overall, our VSANet achieves the best scores on WB-PESQ, composite background, and composite overall, demonstrating its superior performance. Although the composite signal score of our VSANet is slightly lower than that of DMARC and GHNet, it is essential to note that the model size of our VSANet is obviously small than many existing methods. In addition, since our VSANet is causal, the algorithm delay is 32 milliseconds. Meeting the real-time processing requirements, we have also deployed our VSANet on CPU, and the real-time factor is 0.15. In conclusion, we replaced the commonly used STFT by ST-DCT for time-frequency transformation. We designed a multitask learning framework containing a speech enhancement module and a VAD module. In addition, we designed a causal spatial attention block to promote the representation capability of DNN. In the future, we plan to explore even more effective multitask learning schemes. That's all of my presentation, and thanks for your attention.